Lecture 20 covers section 6.6. At the end of today's lecture, you should be able to design and analyze operational amplifiers to process signals. To begin, we'll first talk about what a signal is. A signal can be a voltage or current waveform that is the amplitude of our voltage or current can vary with time that represents some physical phenomena. For instance, our signal could be representing a mechanical measurement, either force, strain, or temperature. For instance, we could use transducers to measure pressure or force on a surface. We could use strain gauges to measure strain, or we could use thermocouples to measure temperature. All of these represent a mechanical quantity to provide us as an input to process. We can also have analog signals that do not come from transducers. An analog signal is one that is a direct output of our measurement device, i.e. everything we have done in this class. For instance, temperature measurement is done using thermocouples, which produce an analog output, and that output is proportional to about 40 microvolts per Kelvin, where our DAC, or data acquisition device, typically requires an input of 0 to 5 volts. For us to amplify our signal, we would have to run our measurement coming from our thermocouple through an operational amplifier to make it readable. Now, before we talk about designing operational amplifiers, we want to introduce the concept of superposition. That is, superposition of linear combinations of signals. Say we have a function f that can take ax1 plus bx2, where a and b are both constants and x1 and x2 are both inputs. If they are linear, i.e. don't depend upon one another, our function can then be expressed as a, our constant, times a function of f1, plus b, a constant, times our function x2. This becomes helpful when we try and sum or subtract signals. For instance, say we have three inputs, x1, x2, and x3, where x3 is a constant, and we want one output, y. Our output then can be formulated as 4x1 minus 2x2 plus 5. Now we notice we have a gain of 4 for x1, a gain of minus 2 for x2, and a constant of 5. All we have to do is apply our proper gains to the system and then sum our signals. To determine the gain of our first input, x1, we could achieve this by using a non-inverting operational amplifier, where we recall our output is equal to 1 plus RF per RL times our input voltage. If we want a gain of 4, we want a ratio of RF per RL to be 3, such that we'll let RF be 30 kiloohms and RL be 10 kiloohms. In doing such, our gain, or our output voltage per input voltage, is equal to 1 plus 30 kiloohms per 10 kiloohms, which gives us a value of 4. Therefore, V2 represents our input and V out represents our output, which would then be x1, our input for our function. Now it's noted that we provided some arbitrary values for our resistors. However, a general rule of thumb is to have your resistors values lie between 5 and 500 kiloohms. Now, if we wanted to determine our gain of minus 2 for the negative 2x2 term within our summation, we would use an inverting operational amplifier. If we recall, our voltage output is equal to minus RF per R1 times our input voltage, we would choose RF to be equal to 20 kiloohms and R1 to be equal to 10 kiloohms. Therefore, our gain would be equal to minus 2. Now, as an aside, what happens if we need a positive gain such that we need a positive value between 0 and unity? Well, we could put two inverting operational amplifiers back to back. Vin would be our input and Vout1 would be our output for our first inverting operational amplifier. Then Vout1 would be our input and Vout2 would be our output for our second inverting operational amplifier. What we could do is, if say we need a value of 0.8, we could set R1, R2, and RF2 equal to 10 kiloohms and RF1 equal to 8 kiloohms. For Vout2 per Vin would be equal to minus RF1 per R1. That would give us our Vout1 term within our expression, where we'd have minus 8 per 10 kiloohms respectively, times RF2 per R2, which would be Vout2 per Vout1 for our second inverting operational amplifier, which would have negative 10 kiloohms per negative 10 kiloohms. And in multiplying our negatives through, we'd see we have a gain of 0.8. such that we can hit that spot that's not typically covered by an inverting or non-inverting operational amplifier. Last but not least, since we have 4x1 and minus 2x2 represented by non-inverting and inverting operational amplifiers respectively, we can use a summing operational amplifier. as denoted on the left. On the left-hand side of the box, we have our three inputs, 4x1 minus 2x2, and 5. And then the sums to one signal, y. This can be represented schematically on the right, where we have V1, i.e. x1, our input into our system connected to a resistor of value R, V2, i.e. x2, our input to our system connected to a resistor R, and all the way down to V sub n, however many number of inputs we have connected to a resistor R. These three resistors are connected at a common node that then goes into our non-inverting terminal of our operational amplifier, and on the bottom they're connected to a resistor that's connected to ground. Our output of our operational amplifier, V0, is connected to a resistor NR, where N represents the number of inputs into our system. It's then connected to a trace that goes into our inverting terminal of our operational amplifier, and then another resistor with resistance R connected to ground. So, if we want our output Y to be 4x1 minus 2x2 plus 5, all we have to do is attach those individual operational amplifier outputs into the input of our summing op-amp. What's nice about this representation, it differs from the one in our text, is that if we keep the value of R the same between our inputs, our resistor is going to ground, and N times R, each input is going to have the same weight. That is, they're going to have the same constant proportionality. That is, our output will be the sum of our inputs, V1 plus V2, all the way up to Vn. So bringing this all together, if we wanted our output to be 4x1 minus 2x2 plus 5, our first input would be that of our non-inverting operational amplifier, where we had V in 1 and V out 1. We would set R2 to be a value of 30 kiloohms and R1 to be a value of 10 kiloohms, such that V out 1, i.e. our input into our summing operational amplifier, is 4 times V in 1. Then for our second input into our summing operational amplifier, V out 2, we would have V in 2 running through an inverting operational amplifier, where it's at R4 is equal to 20 kiloohms and R3 equal to 10 kiloohms. Last but not least, V in 3 would represent our hard offset of 5 volts, and then we can select a value for R5. We'd select R5 such that it's greater than 5 kiloohms, and N times R5 will be less than 500 kiloohms. So R5 would be selected as 10 kiloohms, and then N times R5 would only be 30 kiloohms, which is less than 500. Therefore, output V out from our summing operational amplifier would be 4x1, i.e. 4 times V in 1, minus 2x2, i.e. minus 2 times V in 2, plus 5.